Hi, this is Bill Moore for EV World, where we bring you the future in motion. And today we're going to talk to Omer Bar-Yohay, who is in Israel. I'm sure I murdered that, Omer, but you'll
No,
forgive me. Even
actually,
though,
you did pretty well. You did pretty well, Bill.
okay,
Thank
so
you.
he's in his backyard in Israel via a Skype connection. And as I was explaining earlier, this is probably a better connection than some of the times we've done people here in the United States. So that's great. Technology's working. Anyway, we want to talk about Alice. And for people who aren't familiar with Alice, Alice is their concept for an entirely 100% battery powered, 9 passenger, true crew member, electric commuter airliner. Did I get that right?
You got that perfect. Yes.
Perfect,
Thank you,
right.
Bill.
Part 135 for the FAA aficionados out there. But we do have to talk about on demand, but we'll get around to that in just a minute.
Perfect.
First of all, welcome to EV World. It's a pleasure having you here.
Thanks for having me.
Of course, I think everybody got excited when they saw the illustration of the aircraft that you guys came up with. So let's start off by first of all giving us some background on Eviation.
Okay. So first of all, I think some of the excitement also came from the fact that we have shown a sort of subscale model that's already flying. Most people call it a drone. We call it a model.
Right.
And the reason I think that was interesting is actually the story of Eviation, because Eviation was founded about 2 years ago by myself and a couple of friends in order to bring all electric mobility to the skies. And we thought the best place to start would be general aviation.
There we go.
And that is mostly because we think this is where it makes sense energy-wise. I think a lot of the designs that we're seeing today are very, very old, and general aviation in broader terms did not really evolve as fast as of course not as the computer or internet market, but not
Right.
even as fast as the auto market or anything like that. So we thought that's a place that's ripe for change. But again, making a mistake the size of a 12,000-pound aircraft would have been expensive.
Yeah.
So we figured we're going to build a subscale model that will prove the concept and will show that we're not that far off with the numbers.
Right.
And those were actually surprising for the better. We built a very, very efficient machine that can go at scale. We're talking about a 15 feet wingspan aircraft that goes roughly 150 knots. Which indicates we will be able to fly at 240 knots at the full-scale aircraft. And that was a very, very big deal for us. Eviation, as I said, was founded by three founding partners. I run it today, and the partners are still around, all privately funded. We did it out of passion and out of pocket.
Right.
And of course, we will partner and are partnering with established airframe manufacturers and also with financial partners to actually bring the plane to market. Because once you go big and once you start with the FAA process, things get slightly more expensive.
Yes, they do. Absolutely.
Yeah.
So the drone that you built, I think I saw sort of a photograph of someone holding it, and it sort of looks like it's a little bit different configuration. It's almost from the bottom looks like a Burt Rutan, very
No,
vegan.
no. So probably
So
what you've seen is an old one of the iterations in the beginning. We've been
okay.
testing well, a couple of things. Most importantly, the powertrain was tested on several kinds of drones
Okay.
to really get things in the air without having to really go through the whole process of developing our own airframe from the bottom up. But we did get to the point after about a year of experimenting that we understood that the only way to do it right is really to build something from the bottom up to take, let's say, all the benefits possible out of electric propulsion.
Yeah.
That's why we did this three-pusher configuration, the wingtip propellers and the pusher propeller in the tail, which is kind of, I don't know, some will say weird, we say unique. I think it's something that it kind of grew on us. We understood that this is a way to grab some benefits in drag reduction and in redundancy. And it took us a while to get to that point. Actually, the only drone that was in that configuration was already quite big. It was that 15 feet wingspan thing that still is. It's around 600 pounds maximum takeoff weight, so it's a big machine.
Yeah.
It was introduced for the first time in the Paris Air Show. That was our aim, to sort of show it on stage, and if you will.
Right.
And it actually will start flying missions, not only test flights, in Israel soon enough. We won a tender to supply some basically mapping services, but it's radar mapping services here in Israel for the national company. Mostly because we were able to take the payload and take it fast enough to get a good synthetic aperture radar picture.
Okay.
Where speed is a benefit, and do it very, very cheap. So before the year's end, we will be flying, hopefully, fully certified unmanned missions on that drone. The next step, of course, which is already happening, it's a 2-year step. It's going to take a while, but the next step is, of course, to build a full-scale Alice, and that's, I think, the more interesting notion here. This is what we're here for.
So the surveillance aircraft that you're talking about there, is that the Orca?
Yep, exactly.
Yeah, okay,
we named it the Orca.
Right.
Exactly, and it's a program that was built actually to serve the development of Alice. But as it became interesting for several partners, especially, let's say, civilian purpose mapping and mostly agricultural, what's called precision agriculture today.
Right.
So precision agricultural work, where places where it really matters how much you pay per flight hour.
Right.
We have some very interesting advantages there. So it actually became a program, not just a model that we play with.
Okay. Well, what's interesting, most people don't I could see if you have synthetic aperture radar on this, that this could be valuable for archaeological work.
Absolutely.
I just finished a book actually about some of the archaeological or fraud that has happened in Israel with the I forget, the sort of a tablet supposedly coming from the first temple and some of those things. But what was
it's a very ancient country, so
there's something. Yeah, there's something
plenty real and plenty fake.
Yeah, there's 10,000 archaeological sites that have been mapped in Israel alone.
Yeah.
So I could see where that would be really valuable to the government to identify that, and of course to university archaeologists and people like that to spot things that you couldn't normally spot otherwise. Okay,
I'm with you.
Yeah, so let's talk about Alice then. When I saw the photographs, you've got some things stood out. Obviously, having the pusher props on the wingtips, that's unique. Whereas most aircraft are starting to integrate the winglets, the upturned winglets. Then the enormous butterfly tail, of course, which reminds you of a Bonanza.
Bonanza, or I don't know. I hope the better days of the Bonanza.
The better days of it.
A Bonanza, or if you know the Fuga Magister, the French plane, the French trainer jet.
Trainer jet. Yep. Absolutely.
So, first of all, every Israeli pilot trainee knows the Fuga very well. It's one of the training planes at the flight school. So it threw a lot of memories to a lot of people in my team. And yes, it has a very unique configuration. The configuration is driven from one thing and one thing only. That's cruise efficiency.
Right.
That's practically all we care about. And we said, you know what? We know that there is a history of spin stalls and issues with the butterfly tail. We know that you need to build machines like this very, very carefully. But with today's aerodynamic technology, let's say aerodynamic simulation technology, and with today's advanced avionics and envelope protection, a very, very efficient aircraft that's also safe is doable. Now, one of the benefits that you get when you put those props at the wingtip is that, again, given normal conditions and assuming everything works, your ability to snap out of a spin, or your ability to correct, by the way, even your ability to trim. If you think about it, we're commanding these motors 400 times a second.
Okay.
So you can sense anything that happens to this aircraft and correct at 1/400th of a second in increase of thrust in one of the wingtips. Of course, the moment of inertia on the plane will be significant enough to create correction and actually to increase stabilization as long as you're operating it. The plane is built in a way that it could sustain straight and level flight at any, basically at safe altitudes, and also take off and land safely with either the central prop at the tail
Right.
or the two wingtip props
Okay.
operating, or
What?
all together. Of course, so
Right.
normal conditions it's all together. But if you have an issue anywhere, basically the plane can function with what you would call even better than twin motor redundancy.
Okay. What about,
So
I guess one of my main concerns would be obviously anytime you have two motors either mounted on the wing, near the fuselage, or in this case, unusually out at the tip of the wing, you have an obvious problem with asymmetric thrust. If you lose one of those, if the propeller disintegrates or the engine, the motor freezes or something like that.
one of the first things we tested is a mechanism, or technically it's an electrical mechanism that has to do also a bit with software, but it has been thoroughly tested, and I hope it will be certified on schedule with the rest of the aircraft. Is a mechanism that actually takes out the other motor if you lose one of the wingtips.
Okay.
The idea is very simple. Technically, the airframe can sustain some thrust on one wingtip, and then a lot of correction with it's called the reservator, it's like the tail, the
Right.
butterfly correcting, and then probably you'd be able to go up to almost 50% of thrust in one of the wingtips and still maintain straight and level despite the fact you lost one. But we didn't want to play with it. We
Right.
think there is enough redundancy in the system. We have the tail. The chances of losing both wingtip and a tail at the same time are
Yeah.
ridiculously low. So technically what we do is immediately when you lose a wingtip, it takes under 5 milliseconds to lose the other. It
Okay.
just cuts it out. And then what you get is you get a small bump and you can continue flying on the tail. You also get an instantaneous increase in tail power, and you need to remember that in electric motors, your ability to squeeze extra power from a motor only is dependent on your ability to cool it.
Right.
So in many cases, we are flying. I mean, I think if you look at a normal airframe, you would probably, with a normal propulsion system, of course, you would usually fly at roughly 70 to 75% of your takeoff or your maximum power when you cruise.
Right.
We do roughly 50%. So that
Okay.
gives us a lot of room to play, and
Right.
we use it for safety. That's the whole point.
Okay, good. Well, all of this hinges obviously upon the fact that you're going to have a powerful battery of
Oh
some
yeah.
of some type. Obviously, the Achilles heel here, you got, I think it's on the spec on the website was 980 kilowatt hours.
It's one hell of a battery.
That's more than 10 Teslas.
Exactly, that's 10 Teslas mounted one on top of each
Yeah.
other. Yeah, the point here is actually double, and it needs to be, I think, it needs to be looked at face value, because if you look at today's technologies, and there are plenty of exotics out there, and we love them. I'll talk about them in a minute. But
Okay.
if you look at today's technology, the normal batteries that you can get out of LG Chem or Panasonic or one of those big factories, and soon enough out of the Tesla Gigafactory,
Right.
are those 18650
Right.
cells that will give you roughly 255, maybe 270 watt hour per kilogram.
Right.
And that's more or less what you get. Now, we did not want to wait for anything else to happen. We need something that can be supplied in big quantities. You want to build a pack that size, that's over 70,000
Yeah.
battery cells. That's a lot of welding.
Yes.
Okay, so
Yes.
you don't want to wait for someone who's going to say, okay, I can make 1,000 and 70,000 in 5 years, because how am I gonna fly? How am I gonna supply my plane?
Right.
And how am I gonna certify this? So you want something that's kind of road proven. And this is what we start with. It will make a very, very heavy battery pack. You can do
Yeah.
the math.
Yeah.
Roughly 65% of the maximum takeoff weight is battery.
Is the battery.
That means we have to do everything else extremely light. It is already, I mean, the Orca is already a 65% battery model. This is one of the reasons we built it.
Right.
And what you have to do is you have to build everything else out of the best methods of usage of carbon fiber that you can find. So you'll have a very, very stiff fuselage that's very, very light. So it's like building a very stiff glider
Right.
with the right aerodynamics, of course, and then fitting it with a huge battery. Practically everywhere you touch it. A lot of people say, oh, so where's the battery? Well, it's everywhere.
Yeah.
It's literally everywhere, including seats and wings and whatnot. So the idea is that you just use many small distributed packs. It gives you a lot of redundancy.
Yeah.
It gives you a lot of solutions to what happens if some
Yeah.
part of the battery overheats. You cut it off. It doesn't influence anything but capacity. So you'll have a small light on your dash, if you will.
Right.
It will say, please land as soon as possible.
Yeah.
Will be contained and fire safe because you did not continue to use it, but it will not or no longer be part of the pack. So that's the whole idea. What we did on top of that is one of our biggest supporters and one of the first investors in the company is the founder and owner of an Israeli startup named Finergy, which is a company that makes aluminum air batteries.
Okay.
Now, aluminum air is extremely safe and is extremely energy dense, and maybe it's a little less power dense per weight, but when you're talking about a machine that needs not to do VTOL and then 8-minute flights, but
Right.
you need something that flies 3 hours,
Right.
energy density is the winner.
Right.
So we made some investment in the IP of this company for aviation use.
Right.
And the idea is really to look at what we think at the moment is the most promising technology to take to the air, let's say in the foreseeable future, in the next 5 years or more, and to say we're investing in it, we're investigating it to the level of building systems and flying them, but we understand completely that our clients right now need a good, safe, certifiable aircraft. So we're building it of lithium ion. It gives us ample range for practically any mission that makes sense for the regional airliners, for technically even for us two guys buying a plane, taking the family for vacation, because we can do 600 miles plus IFR reserve, which is alternate plus 45 minutes.
Right.
So that's plenty of time in the air. If you can not go to the bathroom for 3 hours, we can take you there. So that's more or less the deal.
Yeah.
Will we have a longer range version with some exotic battery in 5 or 10 years' time? Absolutely. But we want to have a
Right.
very real life range version in 3 years.
Right.
In 5 years, maybe in commercial flights already.
So let's talk about the specs. What are you're shooting for? 600 miles plus 45-minute IFR reserve.
It's actually 600 miles plus 1 hour because you need to do roughly, let's say, 15 minutes in cruise for alternate,
Right.
and then 45 minutes. It's a tricky one because IFR sometimes changes with the mission. Sometimes your alternate is way further than what you think.
Right.
But this is the idea. We're shooting for this. We are extremely confident we're going to get there. Mostly because of Orca. It gave us a lot of. It gave us, first of all, the execution confidence, but also the sort of proof of concept that you really can't get when you're doing only
Right.
CFD and wind tunnel and all of those experiments. You need to fly.
Yeah.
And the next move for us would be to say, okay, we can do 600 miles and we can do it at an altitude of 10 or 12,000 feet. We're not pressurizing at first stage. The first aircraft will not be pressurized, but it will fly very nicely. The wing loading is high, so it will be stable flight. It goes pretty fast, 240 knots at 10,000 feet is the cruise speed. And you can say it could use, let's say, the rougher part of the general aviation airstrips. We're going to have relatively chubby wheels, so grass landings are an option. The power output will allow a relatively quick takeoff. We're talking about roughly 1,000 feet minimum takeoff weight minimum takeoff length when taking off at full capacity at maximum
Right.
takeoff weight. So it's a very compelling machine. And some of the benefits, and this needs to be understood, some of the reasons are not because we did such a good job. We did. I have a great team. Everything's good. But it's mostly because we started off with electric. your ability to squeeze more energy from the motors and from the battery, and sort of heat up a little for 5, maybe 7 minutes, really gives you the power you need for a very short takeoff, and then for a very quick ascent. So a lot of things happen better because you just build for the mission, and because you're electric, you can do, let's say, more aggressive climbs, more aggressive takeoffs, and so on. One of the other perks of an electric system, we have a powered front wheel motor. So we can taxi from 0 to roughly 20 knots on the ground without, turning the prop.
Something similar to what the EFAN was doing with their motor.
Absolutely. Airbus did it before.
Yeah.
There are companies around that are trying to do this for the big players, for the 787s and so on.
Yeah.
But to do it in an electric, like the EFAN did, is actually very, very smart because you don't use your props when you're wasting energy. Props are terrible at zero airspeed.
Yeah.
And getting it from the ground is basically without any cost. You're spending a couple of pounds more on the system, but that's about it.
Yeah.
So there are plenty of small perks that make sense.
I noticed that it's got kind of an unusually high stance, obviously because of the propellers on the tip of the aircraft.
Yeah, the pushers on the wingtip and on the tail really force us to build a relatively high landing gear.
Right.
It's not perfect. I wish we could have a design that's as efficient, that has an upper wing, and flies as nicely with its props either up front or as pushers.
You could do what some of the sailplanes did and have folding props. Let centrifugal force throw them out.
That's an option. Actually, we did think about it.
Yeah.
I seriously doubt that we can get the kind of packing and the kind of all the props are pitch controlled. So to get pitch control and really a well-packed system, all electric, no hydraulics, and folding, maybe it's an upgrade. At the moment, we're not doing it.